Somewhere beneath the Bay of Naples, something has been building for 19 years. The ground has risen nearly 2 meters. The math that was supposed to describe it no longer works. And the equation that does work, a structure called a finite-time singularity, has a date attached to it that falls within the next 8 years. This is Campiflegrei. 1 million people live inside it, and it did not get its reputation as the scariest volcano on Earth by being subtle. Scientists are not calling this an eruption forecast. They are calling it something harder to explain, and in some ways harder to dismiss: the end of the system's current behavior. Whatever Campiflegrei has been doing for the last 20 years, the numbers say it cannot keep doing it past approximately 2033. Stick with me, because tonight I am going to break down exactly what the math is saying, why 2 completely independent datasets agree on the same window, and what the signals to watch for actually are. Before we go any further, if you enjoy what we do here at Project Nightwatch, make sure to hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you are watching from. Now, let's get into it. Part 1. The equation that shouldn't exist. The ground is moving, not in the way ground usually moves, not the slow geological creep that takes 1 million years to mean anything, but measurably, persistently, acceleratingly, in a way that is now outpacing every mathematical model scientists have trusted for nearly 4 decades. And the people living directly above it number roughly 1 million. Let that sit for a second. There is a place at the edge of the Bay of Naples where the land itself is alive, where the streets crack not because of aging infrastructure, but because the earth beneath them is inflating like something enormous, is breathing under the crust. Where residents have watched their harbour slowly rise out of the water, centimetre by centimetre, year by year, until the boats that once docked there now sit at angles that feel slightly wrong, slightly off, in the way that things feel when something fundamental has shifted, and nobody told you directly. That place is Pozzuoli, Italy. Population approximately 75,000, and it is sitting directly on top of Campiflegrei, which translates, with almost poetic foreshadowing, to the burning fields. Campiflegrei is not a mountain. This is the first thing most people get wrong about it. There is no dramatic cone, no snow-capped peak, no obvious visual threat. Instead, it is a caldera, a collapsed volcanic system roughly 13 kilometers across, formed not by a single eruption, but by the catastrophic implosion of its own magma chamber after a super-eruption roughly 40,000 years ago. The caldera rim now forms the hills surrounding the city of Naples and the Phlegrean Peninsula, and the entire Bay of Pozzuoli sits inside it. The city of Naples itself, population 3 million, lies just outside the eastern rim. So when we talk about Campiflegrei, we are not talking about a distant mountain that might become dangerous. We are talking about a system that already surrounds people, that is already underneath them, that has already been inflating for the better part of 2 decades without pause. Now here is where the story changes. A new study uploaded to the RxEve preprint server this week has done something that the volcanology community is going to be processing for a long time. The researchers took the GPS deformation data from the right monitoring station in Pozzuoli, the most precise and continuous ground movement record available for the region, and they tried to fit mathematical models to it. This is standard practice. Volcanologists fit models to data all the time. They look for the curve that best describes the trend, and then they use that curve to understand what the system is doing. The problem is that the curve everybody has been using doesn't fit anymore. For almost 40 years, the dominant mathematical framework for accelerating volcanic unrest has been a model developed by Barry Voigt in 1988 and 1989. Voigt's method assumes that the rate of change in a volcanic system grows in proportion to the current state of that system, a feedback relationship that naturally produces exponential growth. If deformation is accelerating, you fit an exponential. If seismicity is climbing, you fit an exponential. It works for most systems. It has worked reliably for decades. It is the foundational language of eruption forecasting. At Campiflegrei, the exponential no longer fits, the researchers found that a different mathematical structure, one called a finite time singularity, describes the data with dramatically higher statistical accuracy. And the implications of that word, singularity, are not subtle. A finite time singularity is not just a faster curve, it is a fundamentally different class of mathematical behavior. It describes a system whose rate of acceleration is growing faster than its own current acceleration. It describes a system that is feeding back on itself not just proportionally, but superlinearly. And it describes a system that has, built into its own mathematical structure, a defined endpoint, a moment at which the equations themselves break down. That moment, extracted from the data, falls around the year 2033, with a 95% confidence interval running from 2030.1 to 2034.5. Before you do anything else with that number, let me be extremely precise about what it means and what it does not mean. The researchers are emphatic, not cautious, not hedging, but emphatic, that this is not an eruption forecast. The critical time, or T sub c, as it appears in the equations, does not predict that Campiflegrei will erupt in 2033. What it predicts is that the system's current dynamical behavior, the specific mathematical regime it is operating in right now, will reach its own inherent boundary around that time. What happens at that boundary could be an eruption. It could also be a deflation phase, a regime transition the models have not yet characterized, or something scientists do not currently have a name for. What it cannot be is a continuation of the present trend. The math forbids it. That is what makes this finding so difficult to process. It is not saying the volcano will erupt. It is saying something in some ways more unsettling. The system you are currently watching cannot persist in its current form past this horizon. Something must change. The equations demand it. The two datasets that produce this result are independent of each other, which matters enormously for statistical robustness. The first is the right GNSS station deformation record, essentially a very precise GPS measurement of how much the ground at Pozzuoli has moved vertically over time. Since around the year 2000, this station has recorded upward movement that is not only continuous, but accelerating. The second dataset is the Benioff strain accumulation from regional seismicity, a measure of the cumulative seismic energy being released by the earthquakes that have been rattling the caldera with increasing frequency and intensity. These two datasets, measuring completely different physical phenomena through completely different instruments, both fit the finite time singularity model. Both converge on the same critical window. Both point to approximately the same mathematical horizon. The probability that two independent physical signals measuring different aspects of the same geological system would independently converge on the same critical time range purely by coincidence is not something you dismiss with a shrug. What this convergence is telling you, statistically, is that whatever structure is driving the singularity behavior is embedded in the system itself, not in the measurement noise, not in the model assumptions, but in the underlying physics. And that is the conceptual shift that makes this paper different from previous work on Campiflegrei unrest. Scientists have known for years that something unusual was happening beneath the Bay of Naples. The ground rising more than 1.6 meters since 2005, approaching 5.5 feet of cumulative uplift, was already alarming enough to justify elevated alert levels and emergency planning. But that knowledge was framed, until now, as an unusually intense version of a familiar process, as a really serious Bradyseism episode, as exponential growth, fast and concerning but mathematically conventional. What the new study is saying is that the system has crossed a line, possibly around the year 2022, where conventional descriptions stopped being accurate, where the mathematics of the process changed class, where the system stopped behaving like a faster volcano and started behaving like a different kind of dynamical system entirely. The statistical evidence for this claim is not weak. The inverse time linearization, a transformation that, if a singularity model is correct, should turn the data into a straight line, produces an R-squared value greater than 0.99. That is an almost perfect fit to a straight line across more than 2 decades of data, using multiple different time window selections to verify robustness. An R-squared of 0.99 does not happen by accident. It does not happen because the model is slightly better than the alternative. It happens when the model is describing something real. So let me frame the stakes as clearly as I can before we go further. Inside the Campi Flegrei caldera system, including the surrounding municipalities of the Naples metropolitan area and the Phlegrean Peninsula, approximately 1 million people live, work, and go about their daily lives above a system that is, mathematically speaking, entering a regime it has not occupied since the last time it erupted, which was in the year 1538. The projected uplift at the critical horizon, based on the rate trajectory, approaches 4 meters total. The current uplift is already 1.6 to 1.7 meters. The difference between here and there, in the model's terms, is not a longer version of the same journey. It is a transition to something else entirely. The question the math raises, and that the researchers themselves raise, is not just geological, it is human. What do you do with a mathematical horizon? What does it mean for emergency planning, for population management, for the daily lives of 1 million people, when the equations tell you that the system they are living on top of is approaching the end of its current behavior? And here is the question I want you to hold on to as we go deeper into the data, because it is the question that keeps surfacing in this study. If the system is not building toward an eruption right now, what is it building toward? And how would we know the difference before it was too late to matter? Part 2. The signal beneath the signal. There is a deformation monitoring station in Pozzuoli called Right, and if you were to visit it, it would look almost insultingly ordinary. A small GPS antenna, a metal casing, a data cable. Nothing about it suggests that it is sitting at the apex of something extraordinary. But the record it has been generating since the year 2000 is, in the quiet language of geophysics, one of the most consequential datasets on Earth right now. What Wright has been recording is not just uplift, it is the character of uplift, the shape of it, the geometry of how the ground is moving, which tells you something fundamentally different from how much the ground is moving. Here is why geometry matters. When a volcanic or hydrothermal system inflates the crust above it, the resulting deformation field at the surface spreads outward in a pattern that depends on where the pressure source is and how deep it sits. If you have a centralized, relatively shallow pressure source pushing upward, the surface expression is a bell curve of uplift, maximum displacement at the center, tapering off toward the edges. If the inflation is distributed across a wide region from multiple sources, the pattern looks flatter and more irregular. At Campi Flegrei, the Right station sits at the maximum of that bell curve. Pozzuoli is at the center of a dome of uplift that spreads outward across the entire caldera floor, and the geometry of that dome has remained remarkably consistent, even as its magnitude has grown, which suggests that the pressure source feeding the inflation is not randomly distributed across the system, but is centralized and coherent. There is something down there with a defined location, something focused. That focus matters because it tells you the deformation is not just the diffuse result of widespread geothermal activity or random hydrothermal fluctuation. It has a source, and that source has been pushing upward without reversal for 20 years. But now comes the part that the researchers flag as particularly significant, the part that takes the Right data from interesting to genuinely alarming in its implications. When you compare the rate of surface deformation, the speed at which Right is moving upward, to the rate of seismic energy accumulation in the same time period, you find something unexpected. The seismicity is accelerating faster than the deformation. Let me explain why that is counterintuitive. In a typical volcanic inflation scenario, deformation and seismicity tend to track each other reasonably well. More pressure means more uplift, and more uplift means more cracking of the rocks as they strain under the load, which means more earthquakes. You might expect seismicity to scale roughly with deformation, maybe with some lag, maybe with some local variations. But broadly, if the ground is going up faster, you expect earthquakes to increase proportionally. That is not what is happening at Campi Flegrei. The seismic energy accumulation is running ahead of the deformation rate. It is accelerating on its own trajectory, outpacing what simple pressurization would predict. And this divergence, this decoupling of the deformation field and the seismic field in terms of their rates, is one of the most physically meaningful anomalies in the dataset. What it tells you is that the rock itself is changing, not just deforming, changing. There is a concept in rock mechanics called inelastic deformation, and it is the key to understanding what the data is actually showing. When rock is subjected to stress, pressure from below, in this case, it initially deforms elastically, meaning that if you remove the stress, the rock returns to its original shape. The deformation is temporary, recoverable, reversible, but when stress exceeds a critical threshold, or when it is applied repeatedly over a long enough time, the rock begins to deform inelastically, meaning the damage is permanent. Microfractures form, grain boundaries shift, the internal structure of the rock accumulates irreversible changes. Inelastic deformation creates more fractures than elastic deformation produces. Fractures create pathways for fluids and gases. More pathways mean more fluid migration. More fluid migration means more pore pressure changes in localized zones, which triggers seismicity even in areas that are not currently experiencing maximum deformation. And critically, inelastic deformation means the system has memory. Its current state is not fully described by its current stress level alone, but also by the entire history of stress it has experienced. The faster than expected seismic acceleration at Campi Flegrei is consistent with exactly this transition, a shift from primarily elastic rock behavior to rock that is accumulating irreversible damage. The rock is not just bending under the load, it is breaking, grain by grain, fracture by fracture, in a way that cannot be undone when the pressure eventually changes. And this is what connects directly to the finite time singularity that the new study identifies. A system undergoing elastic deformation is, broadly speaking, recoverable. The mathematics of its behavior can be described by proportional feedback, the Voigt exponential model. But a system undergoing progressive inelastic damage is not simply a faster version of the same thing. It is operating under a different set of physical rule. The feedback is no longer proportional. Damage accelerates the rate of further damage. Fractures create conditions for more fractures. Fluid pathways enable more fluid migration, which drives more pressure changes, which causes more seismicity, which causes more fractures. The system is not accelerating toward a single point of failure from a single source of pressure. It is evolving its own internal failure conditions progressively across the entire rock volume. That is the physical story behind the singularity mathematics. The equation is not just a curve-fitting exercise. It is trying to capture something real about how the system has changed. And that something real is the transition from rock that deforms and recovers to rock that deforms and remembers. Now consider what this means for interpreting the data going forward. If the system has undergone this transition, if the rock of the Campi Flegrei caldera floor is now operating in a regime of progressive inelastic damage, then the relationship between observable signals and underlying physical state has fundamentally changed. An earthquake swarm that would previously have indicated a certain level of pressurization now indicates something more complex, a combination of pressurization and accumulated structural damage. A rate of uplift that would previously have implied a certain volume of new material entering the system now implies a system that is weaker than it was before, responding more dramatically to the same input. The signal is the same. What the signal means has changed. And this is where the study's central contribution becomes clearest. It is not just detecting acceleration, it is detecting a change in the character of the system that the acceleration reflects. The exponential model failed not because the data stopped accelerating, it stopped working because the kind of acceleration changed. The system crossed a boundary in its physical behavior, and the mathematics crossed a boundary with it. What is driving that boundary? What is feeding the irreversible damage accumulation from below? The seismic data has one answer. The chemistry of the fumaroles has another. And when you combine them with the deformation record, you start to see the outline of a machine, a self-reinforcing feedback system that the singularity mathematics is simply describing from the outside. The question of what is actually feeding this machine is the question the data is building toward, and the answer, when it comes, is not what most people expect. Part 3. The 2022 phase shift nobody talks about. There is a specific year buried in the recent scientific literature on Campi Flegrei that keeps appearing in the data without being prominently labelled as significant in most public discussions of the volcano. That year is 2022, and understanding what happened, or rather, what changed, in and around that year is essential to understanding why the finite time singularity model fits the data as precisely as it does. The research by Iacarino and colleagues, published in 2025, provides the clearest articulation of this transition. What they identified, through detailed analysis of both the deformation record and the seismic catalogue, is that around 2022, the Campi Flegrei system appears to have crossed from a regime of predominantly elastic deformation into a regime of predominantly inelastic deformation. The distinction, as I described in the previous section, is the difference between temporary and permanent, between recoverable and cumulative. But let me make this more concrete, because the abstraction can obscure how meaningful this transition actually is. Think about what a volcanic caldera floor does when it inflates and deflates through a series of unrest episodes over decades. In an elastic regime, each inflation episode puts stress on the rocks. The rocks deform. Earthquakes occur as strain is released. Then, if the inflation reverses, if pressure drops, if the system deflates, the rocks recover. Not perfectly, not completely, but substantially. The system partially resets. The next inflation episode starts from a baseline that is not dramatically different from the previous one. Each crisis is, in some meaningful sense, a discrete event with a relatively clean beginning and a relatively clean ending. Campi Flegrei operated something like this during its major Bradysism crises of the 1960s and early 70s, and again during the more intense crisis of 1982 to 1984, when the ground rose nearly 2 meters and approximately 40,000 people were evacuated from Pozzuoli. Those were serious episodes, but they ended, the ground came back down, the system deflated, life returned to something like normal. What began around 2005 was different in duration, but for a long time it was interpreted as a new version of the same pattern, a longer, slower inflation episode that would eventually plateau and reverse, as the previous ones had. The elastic framework was still the assumed baseline. The exponential model was still applicable. 2022 appears to be the year that assumption broke. What the data shows around that time is a qualitative shift in the seismic signature of the unrest. Not just more earthquakes, the character of the earthquakes changed. The frequency magnitude distribution shifted in ways consistent with rock fracturing under stress that exceeds the elastic recovery threshold. The spatial distribution of seismicity began evolving in ways that suggest fracture propagation rather than simply stress release along pre-existing structures. The rate of seismic energy accumulation, relative to the rate of surface deformation, began the faster-than-expected divergence that I described previously. The physical interpretation is that by 2022, the cumulative stress imposed on the caldera rock by nearly 2 decades of continuous uplift had crossed the threshold where elastic recovery was no longer the dominant response. The rock had accumulated enough irreversible damage, enough microfractures, enough permanent grain-scale deformation, enough structural weakening, that subsequent increments of stress were being accommodated by new fracturing rather than elastic strain. The system had transitioned from the behavior of a material under recoverable stress to the behavior of a material under progressive failure. This is why the finite time singularity model, when fitted to the full dataset from 2000 forward, shows such extraordinary statistical coherence. The singularity behavior, the superlinear acceleration, is not an artifact of the entire 20-year record. It is the mathematical signature of a system that has been progressively building toward a damage threshold, crossing it around 2022, and is now operating on the other side of that threshold in a regime where the feedback mechanisms are fundamentally different. Here is the implication that most public discussions have not fully absorbed. Before the 2022 transition, Campi-Flegre's unrest history could be summarized as a series of episodes separated by quieter periods, inflation, partial deflation, relative calm, then new inflation. The system was episodic. Each episode was serious, but the episodes were bounded. There was a template, and the template included recovery. After the 2022 transition, the template no longer applies. The system does not simply recover between cycles in the same way anymore, because the damage accumulated during previous cycles is still present. It is structurally embedded in the rock. The baseline from which each new increment of stress operates is weaker than the baseline from which the previous increment operated. The system is path-dependent now, in a very specific physical sense. Its current state cannot be fully described without reference to everything that came before it. This concept, path dependence in a geological system, has a chilling implication. It means that even if activity at Campi-Flegre were to slow or partially stabilize tomorrow, the system would not return to where it was in 2005. The accumulated damage is not reversible. The weaker rock volume does not unfracture. The system has been permanently changed by the last 20 years, and whatever happens next will happen in a structurally altered caldera that has less resistance to failure than it did when this episode began. And remember, this is what is feeding the mathematics of the singularity, not just the current rate of uplift, not just the current seismicity, but the entire accumulated history of damage that has been building since 2005, crossing a qualitative threshold around 2022, and is now producing the superlinear acceleration that the finite time singularity model captures so precisely. The research consensus has been shifting for several years from treating Campi-Flegre as a system experiencing episodic bradyseism, the traditional term for the rise and fall ground movement that has characterized the caldera for centuries, toward treating it as a system undergoing continuous destabilization. The 2022 transition is the point in the data where that shift in interpretation becomes not just reasonable, but, statistically, the only interpretation that fits. Which brings us to the next question. If the exponential model, the one that works for systems under proportional feedback, has been replaced by a singularity model, what does that tell us about the underlying mechanism? What is it about the physics of this system that produces superlinear rather than proportional feedback? And why did it take until 2022 for the difference to become mathematically unambiguous? The answer starts not at the surface, and not even in the crust, but in the chemistry of the gases rising from deep below. Part 4. Why exponential growth failed. For nearly 40 years, Barry Voigt's failure forecast method has been the closest thing volcanology has to a universal quantitative language. Published in 1988 and extended in 1989, it is a genuinely elegant framework built on a straightforward physical assumption. The rate at which a volcanic system accelerates is proportional to the current rate of activity. In mathematical terms, the time derivative of a measured parameter equals a constant times that parameter raised to some power. If that power equals 1, you get exponential growth. If it is less than 1, you get sub-exponential growth that eventually plateaus. The framework is flexible. It has been validated across dozens of volcanic systems worldwide, and it has contributed to successful eruption forecasts at multiple volcanoes. The reason it stops working at Campi-Flegre is not that the framework is wrong in general. It is that the framework assumes a specific kind of feedback relationship, one where the driving force behind acceleration is proportional to the current state of the system. And at Campi-Flegre, as of approximately 2022, that proportionality has broken down. Here is the clearest way to think about the difference. In an exponential system, if you are at a given activity level, the rate at which activity increases is fixed once you know the current level. Double the activity, double the acceleration. It is a clean, linear relationship between current state and rate of change. The system is not generating acceleration out of anything beyond its current state. In a finite-time singularity system, the acceleration grows faster than the current state would predict. The rate of change is not just proportional to current activity, it is driven by something that itself grows with time, independently of the current observable state. The system is getting an additional push from somewhere. And that additional push comes from the self-reinforcing feedback mechanisms that are built into the physical process of progressive rock damage. The mathematical signature of this is the singularity exponent designated beta. In the Voigt framework, when beta equals 1, you get exponential growth. When beta is greater than 1, you get super exponential growth, the finite-time singularity regime. The researchers found that the GNSS deformation data at Campi Flegrei fits a singularity model with beta approximately equal to 1.4 to 1.5. The seismic Benioff strain data fits with beta approximately equal to 0.6 to 0.7. Now, those two beta values are different, and the difference is physically significant. A higher beta in the deformation data means the uplift is accelerating more aggressively than the seismicity in terms of rate of change. But because we already know that seismicity is outpacing deformation in absolute rate, the combination tells a nuanced story. The deformation system has a higher sensitivity to feedback. It responds more dramatically to each increment of accumulated change. The seismic system is running faster in absolute terms, but has a lower feedback amplification. Both are in the singularity regime. They converge on the same critical time despite their different beta values. And that convergence, despite the different exponents, is the statistical fingerprint of a system that is being driven by a common underlying mechanism that simultaneously affects both its deformation and its seismicity. The inverse time linearization is the key statistical test that confirms the singularity interpretation. Here is how it works. If a finite time singularity model is the correct description of the data, then if you transform the measured parameter using a specific mathematical operation, essentially plotting the inverse of the time remaining until the critical point, the data should fall on a straight line. The better the straight line fits, the stronger the evidence for the singularity model. In the Campi Flegrei data, this transformation produces an R-squared value greater than 0.99. In statistical terms, this is an extraordinarily tight fit. The data is essentially perfectly described by the transformed model across more than 2 decades of observation and across multiple different choices of starting time window. The exponential model, applied to the same data over the same period, does not produce this quality of fit. It produces a curve that progressively underestimates the observed acceleration as you move toward the present. The residuals are not random, they are systematic, meaning the exponential model is not just noisily wrong, but structurally wrong. The shape of the data is not the shape of exponential growth. It is the shape of something steeper, something with an internal endpoint. The conceptual shift required here is not trivial. Most people, when they hear that a volcano is accelerating, imagine a faster version of the same thing. More earthquakes, more uplift, more gas, all trending upward at a growing pace. That mental model implicitly assumes exponential growth. The acceleration is concerning, but it is comprehensible within the familiar framework. You know what exponential growth looks like, where it goes, how fast it gets there. A finite time singularity is different in kind, not just degree. It describes a system that is not simply going faster toward an already understood destination. It describes a system that is moving toward the boundary of its own mathematical description. At the singularity point, at t sub c, the equations themselves formally break down. The variable being tracked formally goes to infinity. In practice, of course, physical systems do not actually reach mathematical infinity. What happens instead is that the governing equations cease to be valid, which means the physical system has undergone some kind of phase transition, some fundamental change in how it is organized and how it behaves. And this is the most important conceptual distinction in the entire study. This is the thing that separates the 2025 findings from everything that has come before. Previous work on Campifligre asked, how fast is the system accelerating, and what does that tell us about the probability of an eruption? The new work asks a more fundamental question. What class of dynamical system is this, and what does the mathematics tell us about when it will change class? The answer, a class change horizon around 2033, does not predict a specific physical event, but it tells you something about the system that no amount of additional exponential model fitting could have told you. It tells you that whatever is currently happening cannot continue as it is. It tells you that the system has an internal clock, and it tells you that the clock is running. The question is, what is winding it? Part 5. The hidden driver. Volatiles, not magma. Here is a fact about Campifligre that tends to get lost in eruption-focused discussions, but is central to understanding the singularity dynamics. The most likely primary driver of the current unrest episode is not fresh magma intruding into the shallow crust. It is gas. Specifically, it is the volatile component, the dissolved gases in the magma at depth, migrating upward into the hydrothermal system that sits between the deep magma body and the surface. And the chemical signature of that migration is being recorded in real time at the Solfatara fumarole field, one of the most extensively monitored gas emission systems on Earth. Solfatara is a small volcanic crater within the Campifligre caldera, and it has been continuously venting sulfurous, carbon dioxide-rich steam for centuries. It is, in the most literal sense, a window into the subsurface chemistry of the system. And what that window has been showing over the past decade is a shift in the ratio of hydrogen sulfide to carbon dioxide in the fumarole emissions, a shift that carries a specific geochemical fingerprint. Here is why ratios matter more than absolute concentrations. The shallow hydrothermal system at Campifligre contains a mixture of gases with different origins. Carbon dioxide can come from deep magmatic sources, from carbonate rock dissolution near the hydrothermal system, or from the hydrothermal fluids themselves as they degas. Hydrogen sulfide is more specifically associated with deep magmatic volatile release. When the ratio of hydrogen sulfide to carbon dioxide rises, it suggests that the deep magmatic volatile contribution is increasing, that more gas is arriving from depth, bypassing or overwhelming the shallow hydrothermal scrubbing that would normally remove hydrogen sulfide before it reaches the surface. This is the signal that has been changing at Solfatara. The rising H2S to CO2 ratio is not proof of new shallow magma intrusion, but it is consistent with and strongly suggestive of an increase in deep volatile release, the degassing of magma at depth pushing more gas upward through the crust, through the hydrothermal system, toward the surface. And this matters for the singularity mathematics because of the physical mechanism by which deep volatiles drive surface deformation and seismicity. When hot, high-pressure gas rises through rock, especially fractured or partially fractured rock in a hydrothermal setting, it does several things simultaneously. It increases pore pressure in the rock matrix, which has the effect of reducing the effective normal stress on fracture surfaces. Reduced effective normal stress means fractures that were previously locked by friction can now slip. Slipping fractures are earthquakes, so volatile migration directly triggers seismicity, even without any accompanying magma movement. But there is a second, more insidious mechanism. Hot acidic fluids and gases, particularly sulfuric acid, produced from hydrogen sulfide oxidation in the shallow system, are chemically corrosive to rock. They attack the silicate mineral structure at fracture surfaces, a process called stress corrosion. Stress corrosion weakens fracture surfaces, reduces the friction coefficient, and makes the rock more susceptible to slip at lower stress levels. Over time, and especially under sustained volatile flux, This chemical weakening compounds the mechanical weakening from inelastic deformation. The rock is not just being damaged physically, it is being corroded chemically. This combination, mechanical damage accumulation plus chemical weakening, creates the conditions for exactly the kind of self-reinforcing feedback that the singularity model describes. More volatile flux means more pressure, more seismicity, more fractures, more permeability, which allows even more volatile flux, which creates even more pressure, and so on in a loop that is not simply proportional, but amplifying. There is an important nuance here that the researchers are careful to maintain. The surface signals at Solfatara are a mixture of deep and shallow processes, and separating them is genuinely difficult. The CO2 to water vapor ratio in the fumaroles also carries information about the hydrothermal system itself, about its temperature structure, about the depth at which phase separation between vapor and liquid occurs. Attributing any single geochemical observation to magmatic versus hydrothermal origin requires careful modeling and carries significant uncertainty. What the data supports is not a clean, unambiguous, deep magmatic signal. What it supports is an increasing contribution from deep in the system, whether that is interpreted as volatile degassing from a deep magma body or as heat and fluid input from a slowly rising magmatic intrusion that has not yet reached shallow depths, or as some combination of both. The ambiguity is real. But the direction of the trend toward deeper, hotter, more magmatically influenced volatile input is clear in the geochemical record. And this is what the finite time singularity is responding to, not a sudden injection of new magma, not a discrete intrusion event that could be identified and tracked in real time, but a gradual, sustained, and now apparently accelerating increase in the deep volatile flux that is feeding the hydrothermal system, and, through that system, the mechanical and chemical weakening of the caldera rock. The system is being driven from below. It is being driven invisibly, in the sense that there is no obvious surface eruption precursor, no lava, no ash, no dramatic seismic crisis of the kind that would trigger immediate evacuation. It is being driven by something that operates on a timescale longer than a single crisis, longer than a single year, and that has been building since before the current unrest episode began. And the central narrative the data tells is this: the system is not just accelerating, it is coupling. The deformation, the seismicity, the geochemistry, they are becoming increasingly integrated, increasingly mutually reinforcing, increasingly described by a single coherent mathematical structure. That coupling is what the singularity captures, and understanding how tight that coupling has become requires looking at one more layer of analysis that the new study introduces and that changes how you think about cause and effect in volcanic systems more generally. Part 6. Transfer entropy. What is actually driving what? One of the most common assumptions in volcanic hazard monitoring is that seismicity is a leading indicator. Earthquakes happen, and then things escalate. You watch the earthquake catalog, you track the swarms, you analyze the locations and mechanisms, and you use all of that to infer what the magmatic system is doing and where it might be going. Seismicity, in this framework, is the canary in the coal mine. It tells you what is coming before you can see it any other way. At Campi Flegrei, the new study inverts this assumption using a method called transfer entropy analysis, and the result is one of the most conceptually disruptive findings in the paper. Transfer entropy is a statistical technique borrowed from information theory that measures the directional flow of information between two time series. Specifically, it asks, does knowing the recent history of variable A help you predict the future state of variable B better than knowing the history of B alone? If it does, then there is a causal information flow from A to B. Crucially, the test is directional. You can ask whether A drives B, whether B drives A, or both, and get statistically separable answers. When the researchers applied this technique to the Campi Flegrei dataset, analyzing the relationships between GNSS deformation, seismicity, and the geochemical volatile ratios, the results were unambiguous and directionally specific. The causal flow from GNSS deformation to seismicity is strong and statistically significant. The reverse flow from seismicity to deformation is weak and not statistically significant. The causal flow from the hydrogen sulfide to carbon dioxide ratio to seismic acceleration is measurable as a secondary driver. What this tells you, in plain terms, is that at Campi Flegrei right now, seismicity is not driving the system. It is a response to the system. The earthquakes are outputs, not inputs. They are generated by the deformation and the volatile flux, not generating them. Let me explain why this is so conceptually significant, because it is easy to read that and nod and miss the implication. Traditional volcanic monitoring protocols, particularly for systems like calderas where there is no obvious edifice to instrument, lean heavily on seismicity as the primary escalation signal. Earthquake, swarms trigger, alert level reviews. Seismic energy release rates feed into probabilistic eruption forecasting models. The entire architecture of risk communication is built on the implicit assumption that when seismicity increases, the system is becoming more dangerous, and when seismicity is relatively quiet, you have some buffer. At Campi Flegrei, if the transfer entropy result holds, that architecture may be partially inverted. The real driver is the deformation, the continuous, accelerating inflation of the caldera that reflects the pressure and volatile input from depth. Seismicity is tracking that inflation, responding to it, generated by it. This means that a period of relatively lower seismicity would not necessarily indicate that the system is less dangerous if the deformation was still accelerating. The silence might simply mean the rock is deforming elastically at that moment, temporarily, reversibly, before the next cascade of fracturing begins. More disturbing is the implication for the transition from acceleration to crisis. In a seismicity-led system, you expect to see a dramatic increase in earthquakes before the critical failure, a seismic precursor that gives you warning time. In a deformation-led system with seismicity as a lagging response, the precursor sequence may look different. The key escalation signal may be in the deformation rate, not in the earthquake count, and the deformation is already in a singularity trajectory. The hydrogen sulfide to carbon dioxide ratio, appearing as a secondary driver of seismic acceleration, is also meaningful. It suggests that as the chemical volatile signature shifts, as the deep magmatic input to the hydrothermal system increases, the seismic response tightens. Geochemistry is not just a passive indicator, it is feeding back into the seismic system. The deeper the volatile source, the more the seismicity responds. And the more the seismicity responds, the more fracturing occurs, which increases permeability, which allows more volatile migration, which changes the geochemistry further. The system hierarchy that emerges from the transfer entropy analysis is therefore deformation at the top, driven by pressure from depth, volatile chemistry as a secondary driver, modulating the seismic response, seismicity at the bottom as the observable expression of stress accommodation in the damaged rock volume. The whole structure couples together, and the coupling is tightening as the system approaches its mathematical horizon. What this means for forecasting is subtle but important. The researchers are not saying that seismic monitoring is useless. They are saying that seismicity alone is not the right variable to watch for the primary escalation signal. You have to watch the deformation. You have to watch the geochemistry, and you have to watch the relationships between those variables, the coupling strength, the directional information flow, the degree to which the system is becoming more internally coherent, because that coherence, that tightening of the feedback loops, is what a finite time singularity looks like from the inside as it approaches its critical horizon. The system is not just getting louder, it is getting more organized. And organized systems, in the physics of complex dynamical behavior, are more capable of coordinated failure than noisy, diffuse ones. The question of where the system currently sits on the spectrum between accelerating but incoherent and synchronized and ready for coordinated failure is the most important diagnostic question the new study raises. And the answer, at least for right now, carries a small amount of genuine reassurance. but only if you understand exactly what is missing from the current signal. Part 7. The feedback loop that creates a singularity. Let me build the machine for you step by step, because understanding the physical loop that produces the singularity mathematics is the only way to understand both why the math is so compelling and why the outcome remains genuinely uncertain. It starts at depth. Somewhere below the caldera floor, probably at depths between 3 and 8 kilometers, though the estimates vary, there is a body of partially molten rock, not a lake of liquid magma, but a crystalline mush, hot and partially molten, under enormous pressure, containing dissolved gases that want to escape: carbon dioxide, water vapor, sulfur dioxide, hydrogen sulfide. These gases are held in solution by the pressure of the overlying rock column, but pressure and temperature change over time. The system evolves, and as it does, some of those gases exsolve. They separate from the melt and begin migrating upward through the rock as a separate fluid phase. This volatile injection is step 1. It is the input signal. It is, as best the geochemical evidence can tell us, increasing over the current unrest episode. Step 2. The rising volatiles enter the shallow hydrothermal system, which sits above the deep magmatic reservoir at depths of roughly 1 to 3 kilometers. This system is a complex network of fractures, pore spaces, and hot water that mediates between the deep magma and the cool, shallow crust. The influx of additional volatiles from below increases the pressure in this hydrothermal system. Hot, pressurized fluid occupies more volume than cool fluid. The rock above the hydrothermal system must accommodate that volume change. It inflates. Step 3. The inflation. The surface above the pressurizing hydrothermal system rises. RITE records the uplift, centimeter by centimeter, year by year. The rock under tension, the crust being domed upward by the pressure below, accumulates elastic strain. Up to a threshold, this strain is recoverable. Beyond the threshold, it becomes inelastic. Fractures form, permanent damage accumulates. Step 4. Seismicity. As the rock fractures under the accumulated stress, both the tensile stress from above and the shear stress along pre-existing fault structures, it releases energy as seismic waves. Earthquakes occur. The fractures created by those earthquakes are not closed after the event. They remain as permanent pathways in the rock. The rock has been structurally altered by the earthquake that expressed its damage. Step 5. Increased permeability. The new fractures created by seismicity are conduits. Hot fluid and gas from the hydrothermal system can now flow through rock volumes that were previously less permeable. The network of pathways connecting the deep pressure source to the surface has expanded. More fluid can move, more pressure can be transmitted upward, more volatile gas can reach the hydrothermal system and beyond. Step 6. This closes the loop. More permeability means more volatile flux from depth can be accommodated by the hydrothermal system. More volatile flux means more pressurization. More pressurization means more deformation. More deformation means more inelastic damage, more fractures, more earthquakes, more permeability increase. The cycle is self-reinforcing. Each iteration does not simply repeat the previous one. It starts from a slightly more damaged, slightly more permeable, slightly more connected rock volume. The baseline shifts with each cycle. The feedback is not proportional, it is multiplicative. This is the physical engine of the finite time singularity. The singularity mathematics is capturing, in abstract form, this physical loop. The singularity exponent beta greater than 1 is telling you that the feedback amplification is growing faster than the current state, which is exactly what you get in a system where each cycle of the loop creates a slightly more favorable condition for the next cycle. The critical phrase here is multiplicative feedback. In an exponential system, feedback is proportional. It adds a fixed fraction of the current state back into itself with each cycle. In a singularity system, feedback is multiplicative. Each cycle adds a fraction that is itself growing because the system's internal state has become more efficient at transmitting the feedback. The damage accumulation, the permeability increase, the tightening of the connection between deep volatile source and surface expression, all of these are mechanisms that make each loop iteration slightly more powerful than the last. Now, here is the feature of this loop that makes it qualitatively different from a simpler accelerating system. The instability it creates is distributed. The damage is not concentrated at a single fracture, not building toward a single failure surface that, when it slips, releases everything. Instead, the damage is spreading across the entire rock volume of the caldera floor, diffuse fracturing, widespread permeability increase, chemical weakening occurring wherever hot acidic fluid is now flowing. The system is not approaching a single point of catastrophic failure. It is building the conditions for coordinated failure across a large, spatially distributed volume. And this distributed nature has a specific mathematical signature that the researchers look for in the data as a diagnostic of how close to coordinated failure the system actually is. That signature is called log periodic oscillations, and its absence from the current Campi-Flegrei dataset is one of the most important findings in the study, and the reason why the critical horizon around 2033, while it represents the end of the current regime, does not currently indicate an imminent, large-scale eruption. Part 8. Why there is no imminent eruption signal yet. Log periodic oscillations are a feature of complex systems that are approaching a critical transition through hierarchical fracture propagation. The term is technical, but the concept is intuitive. Imagine a material under stress that is failing not all at once, but through a cascade of fractures, each larger than the last, propagating upward through scales from microscopic grain boundaries to mesoscopic rock volumes to the macroscopic structure of the entire system. As this cascade proceeds, the way the system oscillates around its accelerating trend follows a specific mathematical pattern, oscillations whose frequency increases as you approach the critical point, but whose frequency increases in a specific multiplicative ratio, a logarithmic periodicity. These log periodic oscillations appear in the seismic and deformation data of systems that have developed what physicists call hierarchical fracture coordination, where damage at small scales is being organized and amplified by damage at larger scales in a cascading network. They are the mathematical fingerprint of a fracture network that is becoming self-organized, that is developing the connectivity needed to coordinate failure across the system. At Campi-Flegrei, as of the dataset analyzed in the new study, these log periodic oscillations are not present in the data. The seismicity is accelerating, and it is accelerating in a way that fits the singularity model, but the acceleration does not show the hierarchical oscillatory pattern that would indicate coordinated fracture propagation. This is not a minor technical detail. It is a diagnostic of system state that has direct bearing on the probability of a near-term large-scale event. The absence of log periodic oscillations tells you that despite the singularity class acceleration, the seismicity is still spatially diffuse. The earthquakes are distributed across the caldera rather than clustering along a developing failure surface. There is no connected fracture network that has achieved the spatial coherence needed to coordinate a large rupture or to create a conduit for rapid magma ascent. In the language of complex systems physics, Campi-Flegrei is currently in what you might call the intermediate phase, beyond the stability of fully recoverable elastic deformation, but not yet at the organized criticality of hierarchical fracture coordination. It is in the transition zone between stability and catastrophic potential. It is unstable, but it is not yet synchronized. This distinction matters enormously for how you interpret the singularity result. The critical horizon around 2033 is not, in the researcher's interpretation, a countdown to eruption. It is the projected end of the current regime, the point at which the dynamics as currently described must undergo some kind of qualitative change. What change that is depends on how the system evolves between now and then. One possible trajectory is continued acceleration toward genuine synchronized criticality, the development of log periodic oscillations, fracture network connectivity, and ultimately a large-scale failure event that could include an eruption. This is the trajectory that justifies the most alarming interpretation of the singularity result. A second possible trajectory is deflation or regime change before the critical horizon is reached. Some process, possibly the exhaustion of the deep volatile supply, possibly a change in the hydrothermal system's thermal structure, possibly an external perturbation that arrests the feedback loop before it reaches the singularity boundary. This is what happened in previous Campi Flegrei unrest episodes, though under very different physical conditions and with much less accumulated damage. A third possibility, and one that the researchers explicitly acknowledge, is a transition to a regime that current models do not adequately describe, something that is neither eruption nor simple deflation, but a restructuring of the system that the singularity mathematics can identify as a boundary without being able to characterize what lies on the other side. The point is not that the outcome is predetermined, the point is that the current regime is bounded. The mathematics has identified a horizon. What matters now, for science, for monitoring, for emergency preparedness, for the 1 million people whose daily lives are conducted above this system, is what signals will indicate which of these trajectories the system is taking. And those signals are specific. They are identifiable. They are not mysterious, but they require watching the right variables in the right ways, which is something that the conventional seismicity-focused monitoring framework may not fully capture without the kind of integrated, multivariable, physics-based analysis that the new study represents. Part 9. What T sub C actually means. The year 2033 has now appeared several times in this discussion, and I want to be as precise as possible about what that number represents and what the range of physical outcomes it encompasses actually includes, because the gap between the math points to this date and something specific will happen on this date is enormous, and collapsing that gap is how misinformation begins. The critical time, T sub C, is a parameter extracted from the finite time singularity model fitted to the data. In the mathematical framework, it is the time at which the model's predicted value of the monitored variable formally diverges to infinity, the singularity point. In practice, of course, no physical variable goes to infinity. What the singularity in the model represents is the breakdown of the model's validity, the point at which the equations governing the system's current behavior cease to describe it. Think of it this way. Water behaves according to a specific set of physical laws when it is in liquid form. It flows, it has a measurable viscosity, it conducts heat in specific ways. Those laws are valid until the water reaches a phase transition boundary. At the phase transition, boiling, freezing, the laws change. New governing equations apply. The old equations are not wrong in their domain, but their domain has ended. The phase transition is the boundary. T sub C for Campi Flegrei is that kind of boundary. The singularity model's validity ends there. What lies on the other side is not specified by the model. It is only specified as not what we are currently observing. The current dynamical regime, progressive accumulation of inelastic damage under accelerating feedback from deep volatile flux, producing superlinear growth in deformation and seismicity, cannot continue past this horizon. Something must change. Now, what are the possible somethings? The researchers enumerate them clearly. First, an eruption, the most dramatic and most obvious phase change, in which the accumulated pressure and structural damage in the caldera finds a pathway to the surface. This is the outcome that drives evacuation planning and dominates public discussion. Second, a deflationary phase, in which the deep volatile input decreases, the hydrothermal system loses its pressure driver, and the accumulated deformation partially reverses. This happened, after a fashion, following the 1982 to 84 crisis and following earlier episodes. Under current conditions, with the accumulated structural damage of 2 decades, a deflationary phase would look very different from previous ones. It would not be a clean recovery. Third, a regime transition that is neither eruption nor simple deflation, perhaps a reconfiguration of the fluid pathways in the hydrothermal system. Perhaps a large-scale subsurface structural failure that releases pressure without producing a surface eruption. Perhaps something that has not been observed in the current monitoring era. The uncertainty here is genuine and significant. The singularity model tells you with high confidence that the current trajectory terminates around 2033. It does not tell you what replaces it. This is mathematically analogous to a weather forecast that tells you with high confidence that tomorrow's conditions cannot persist for another week. The current atmospheric pattern is unstable and must transition without being able to specify exactly what the new pattern will be. But there is something important about how this uncertainty should be received. It is not the same as saying we have no idea what will happen. It is saying we know the boundary is real, we know it is approaching, and we know that what matters now is tracking the indicators that will distinguish between possible outcomes. That is a more sophisticated and more action-oriented uncertainty than the simple "we don't know" that often gets assigned to complex geophysical questions. The confident interval of 2030.1 to 2034.5 at the 95% level means that the statistical analysis is very tight around the 2033 central estimate. The window is about 4 years wide at the extremes. This is not a horizon far enough away to be dismissed as someone else's problem. For the Italian civil protection authorities, for the residents of Pozzuoli and the surrounding municipalities, for the volcanologists who study this system, it is a planning horizon that is already inside the near-term future, and the physical meaning of approaching 4 meters of total uplift projected at the singularity boundary based on the current rate trajectory gives the abstract mathematics a concrete human geography. Pozzuoli sits at the center of the deformation field. 4 meters of additional uplift from the current 1.6 to 1.7 meters means infrastructure strains that compound those already being observed. It means coastal flooding geometries that change as the harbor continues to rise from the sea. It means geological deformation on a scale that has physical consequences for the built environment of a city of 75,000 people that is already experiencing the effects of the current uplift. The boundary approaching in the equations is not abstract. It has a physical address. That address is a harbor in the Bay of Naples, where the columns of the Roman fish market, the Macellum of Pozzuoli, bear the borings of marine mollusks at heights of nearly 6 meters above their current waterline, fossil evidence of how much higher the sea level was relative to the ground when the caldera was previously submerged during an earlier cycle of Bredicizum. The system has been here before, in some sense, but the current trajectory suggests it is approaching that boundary faster and from a more structurally compromised starting point than any episode in recorded history. Part 10. The Predictability Paradox. Here is one of the most counterintuitive findings in complex systems science, and it applies directly to what the new study is showing about Campi Flegrei. As a singular system approaches its critical horizon, the mathematical precision of the forecast paradoxically decreases. The closer you get to T sub c, the less certain you can be about the exact timing and nature of the transition. More data, in a very specific sense, produces more uncertainty rather than less. This sounds like it should not be true. Shouldn't more observations narrow down the range of possibilities? Shouldn't a longer, richer dataset allow a more precise forecast? In a normal statistical context, yes. In the context of a finite time singularity, no. And the reason is fundamental to the mathematics of the framework. As the system approaches T sub c, it becomes increasingly sensitive to small perturbations. The same small input, a slightly higher volatile flux, a slightly larger seismic event, a minor change in the hydrothermal system's thermal structure, produces a much larger change in the system's trajectory near the singularity than it would produce far from it. This is called sensitivity amplification, and it is a mathematical property of all singular systems. Near the singularity, tiny differences in initial conditions map to vastly different outcomes. This means that as you add more data, as you observe the system in the weeks and months closer to T sub c, the range of possible physical outcomes actually expands rather than contracts. The system's behavior near the boundary is more sensitive to the specific path it has taken, which is more sensitive to small fluctuations, which means more uncertainty about where precisely it will end up. The forecast horizon for a singular system shrinks as you approach the singularity. The good predictability window, the range over which the model can give reliable guidance, gives way to a limited predictability zone in which the forecast's confidence interval grows despite growing data. The researchers explicitly introduce this concept using what they call trust horizons. There is a time range over which the singularity model gives useful, reliable guidance, and that range is approximately now to 2028 or so, based on the current data. Beyond that, as T sub c approaches, the sensitivity amplification takes over, and the specific physical outcome becomes progressively harder to pin down. This creates a paradox that is genuinely psychologically uncomfortable. The period when scientists will know the most about the system, the months and years closest to the critical horizon, when they have the densest monitoring data, the most refined model parameters, the most detailed observations, will also be the period when the precise outcome is least predictable. Knowledge and uncertainty will increase together. This is not a failure of science. It is a mathematical property of the kind of system Campi-Flegrei appears to be. It is telling you something important about the nature of complex nonlinear dynamics near criticality, but it means that the window for meaningful intervention in terms of emergency planning and population preparedness is not wait until the data is really clear and then act. The window is now, while the system is in the more predictable phase of its approach. Waiting for the picture to clarify is, in this mathematical framework, waiting for it to become simultaneously clearer in some respects and more uncertain in the ones that matter most. This is what makes the 2025 paper so consequential as a policy document, even though it is written as a scientific analysis. It is telling the people responsible for the safety of 1 million residents that the optimal decision window for preparation is the current period, not because the outcome is known, but because the mathematical framework predicts that the preparation window will narrow, not expand, as time passes. And this brings us, necessarily, to the history of this system, because understanding why this moment is unprecedented requires understanding every previous moment that seemed unprecedented at the time, and how each of those previous moments fell short of what the current data is showing. Part 11. Historical context. Why this time is different. Campi-Flegrei has a long history of alarming its residents. The Roman poet Virgil identified the area around Lake Avernus, a crater lake within the caldera, as the entrance to the underworld. The ancient Greeks called the whole region the Phlegrean Fields because the sulphurous vents and boiling mud pits seemed to them like evidence of subterranean fire. For thousands of years, the ground has risen and fallen, the fumaroles have vented, the earthquakes have rattled, and human civilization has continued on top of it all because the eruptions, when they came, tended to be localized and, by volcanic standards, relatively manageable. The last eruption was in 1538. It was called Monte Nuovo, New Mountain, because a new cinder cone, approximately 140 meters high, appeared overnight, formed by an eruption that lasted about a week. The eruption was preceded by several decades of significant ground uplift and an intensification of seismicity in the days and hours before the eruption began. Accounts from the time describe the sea receding from the shore of Pozzuoli before the eruption, suggesting rapid ground uplift in the immediate precursor period. Approximately 24 people were killed, mostly those who had come to observe the newly formed ground feature shortly after the initial phase, and were caught by a later paroxysmal phase. This eruption is significant not because it is large, by geological standards, it was a small event, but because it represents the last time the Campi-Flegrei system released pressure through a surface eruption. Everything since 1538 has been subsurface: inflation, deflation, seismicity, fumarolic activity, but no eruption. The question of why the system has not erupted again despite multiple major unrest episodes is itself scientifically interesting, and the answer likely involves the specific geometry and state of the magmatic hydrothermal system at each crisis point. The major documented Brdyseism crises of the 20th century provide the best comparison points for the current unrest. The episode of 1969 to 1972 produced approximately 170 centimeters of uplift. The more severe crisis of 1982 to 1984 produced an additional 162 centimeters of uplift, and in the months of peak activity, the rate was intense enough that the Italian government ordered the evacuation of approximately 40,000 people from central Pozzuoli. That evacuation, involving the displacement of tens of thousands of people from their homes, the partial emptying of an ancient city, the logistical and social trauma of a major forced relocation, was the most dramatic consequence of Campi Flegre's recent unrest history. And it happened without an eruption. The system deflated, the ground came back down, and Pozzuoli was eventually re-inhabited. What followed was a long period of relative quiet, punctuated by minor unrest, until approximately 2004 to 2005, when the current uplift episode began. Since then, the ground has risen approximately 1.6 to 1.7 meters with no significant sustained reversal. The cumulative uplift since 2005 already exceeds the total from either of the two 20th century crises individually. But the comparison that matters is not just in terms of magnitude, it is in terms of structure. The 1969 to 72 and 1982 to 84 episodes were relatively compact in time, intensive crises lasting months to a few years before deflation began. They were episodic. They had clear boundaries. The current episode has now been running for 20 years. It is not episodic. It has no clear boundary. And critically, it has not deflated. The two previous major crises occurred in a system that had not yet accumulated 20 years of continuous inelastic damage. They occurred in a caldera rock volume that still had significant elastic recovery capacity. The crisis of 1982 to 84 pushed the system hard, but did not leave it fundamentally altered in the way that 20 years of continuous loading has done. The Monte Nuovo eruption of 1538 offers a different kind of comparison, not as a structural analogue, but as a reminder that the system is capable of eruption when the conditions are right. The preceding period before 1538 involved ground uplift episodes documented through the marine boring evidence in the Macellum columns, which suggest that the caldera had been in a prolonged period of inflation before the eventual eruption. The exact duration and rate of that prehistoric uplift is uncertain, but the system demonstrated that it can move from prolonged inflation to eruption when some threshold is crossed, and the current episode, in terms of both duration and accumulated deformation, is entering the territory of the longer-term preparatory periods documented in the geological record. This is why the 2025 study frames its finding as the system entering a regime not seen since 1538. Not because an eruption is expected, the mathematics explicitly do not support that specific claim, but because the combination of duration, accumulated damage, current rate of acceleration, and projected trajectory over the next decade places the system outside the range of anything in the modern monitoring era. The 20th century crises, alarming as they were brief enough and elastic enough that they did not leave the system in a structurally analogous state to where it now sits. The current episode has no modern precedent. The only analogous period in the system's documented history is the one that eventually produced a new volcano. Part 12. The 4-meter threshold. The number 4 meters appears in the study as the approximate projected uplift at the critical horizon, extrapolated from the singularity trajectory. The current total uplift since 2005 is approximately 1.6 to 1.7 meters. The difference, roughly 2.3 to 2.4 additional meters of ground rise projected over the next several years, is not an arbitrary threshold. It is a number with physical and human consequences that are worth examining in concrete terms. 4 meters of total uplift from the 2005 baseline means that the center of Pozzuoli, already visibly higher above sea level than it was 20 years ago, will have risen to a point at which the coastal geography of the Bay of Pozzuoli is significantly altered. The harbour area, already experiencing the effects of the current uplift in terms of changed dock geometries and altered coastal drainage patterns, would face continued transformation. The infrastructure of a city built to its current elevation relationships with the sea and with the surrounding landscape would be operating in a geometrically different environment. But the physical geography is almost a secondary consideration compared to the structural implications for the rock volume itself. 4 meters of cumulative uplift from a deep, pressurized source represents a very large amount of elastic and inelastic strain in the crust above that source. The volume of crust that has been permanently deformed by the current episode is already substantial. At 4 meters total, it would represent a deformation state that has very few analogues in modern volcanic monitoring records globally, certainly none for a system of this scale and population density. The population exposure figure, approximately 1 million people within what scientists define as the caldera system's hazard zone, includes not only Pozzuoli and the other municipalities directly on the caldera floor, but the eastern portion of Naples, the densely populated coastal communities of Bagnoli, Bacoli, Monte Procida, and Ischia, and the broader Naples metropolitan area that lies just outside but downwind and potentially within reach of any significant eruptive event depending on scale and style. The scale of a hypothetical eruption at Campi Flegrei is one of the most important and most uncertain variables in the entire discussion. The geological record shows that the system is capable of enormous eruptions. The Campanian ignimbrite supereruption roughly 40,000 years ago is among the largest volcanic events in European geological history, responsible for a layer of ash found across much of Europe and the Middle East. The Neapolitan yellow tuff eruption, approximately 15,000 years ago, was also enormous. These were caldera-forming events at a scale that modern civilization has no contingency framework for. But the system is also capable of far smaller events. Monte Nuovo in 1538 was, on the scale of Campi Flegrei's history, a minor event. Many volcanic systems cycle between small, moderate, and occasionally catastrophic eruptions, and the probability of any specific scale of event is a function of conditions at the time rather than a fixed characteristic of the system. The current state, prolonged inflation, accumulated damage, deep volatile flux, does not in itself specify eruption scale. It specifies that the system is under unusual stress. What happens to that stress and how it is released determines scale. What the 4-meter threshold represents, then, is not a specific physical event. It is a marker of how far the system will have been pushed by the time it reaches its mathematical horizon. It is the accumulated weight of 25 to 30 years of continuous inflation, expressed as a single number that encapsulates the degree of departure from the historical baseline. It is, in the terminology of complex systems, a measure of how far from equilibrium the system will be when the current regime terminates. Far from equilibrium systems, when they transition more dramatically than systems close to equilibrium. This is not a subtle point. It is one of the most robust findings in the science of complex dynamical systems. The further from equilibrium, the more energy is available for the transition, and the more dramatic the transition tends to be. The 4-meter projection is not just a height, it is a measure of energy storage. It is a measure of how much potential the system will have accumulated by the time something changes. Part 13. The Conspiracy Gravity Well. Any discussion of Campi Flegrei that circulates beyond academic volcanology quickly attracts a set of narratives that have nothing to do with the actual science and everything to do with the peculiar way that genuine alarm, filtered through social media and pattern-seeking cognition, generates alternative explanations. It would be irresponsible not to address them directly, because some of them are actively misleading people about what is real. The most common alternative narrative is suppression, the idea that Italian authorities, or some broader international scientific establishment, are concealing the true severity of the situation from the public to avoid panic. This narrative misunderstands how Italian volcanological monitoring actually works. The INGV, Istituto Nazionale di Geofisica e Vulcanologia, publishes its monitoring data openly. The GNSS deformation records, the seismic catalogues, the geochemical measurements from Solfatara, all of this is publicly available and has been used by researchers at multiple independent institutions to produce the kind of analysis the new study represents. The paper itself was uploaded to Araxiv, which is a public preprint server specifically designed to make research available before formal peer review. If there were a suppression campaign, it is operating with extraordinary incompetence. The second category of narrative involves artificial causation, claims that the current unrest is being generated or amplified by human activity, whether industrial, military, or technology-related. This runs into a fundamental problem of scale. The energy involved in inflating the crust above a large volcanic system by 1.6 meters over 20 years is in round numbers, on the order of 10 to the 18th joules, roughly equivalent to thousands of nuclear warheads detonating simultaneously and continuously for 2 decades. The entire global energy consumption of human civilization per year is approximately 6 times 10 to the 20 joules. There is no human-scale activity that could generate and sustain the kind of deep crustal pressurization that the monitoring data records. The scale simply does not allow for it. But the more interesting and more dangerous misinterpretation is not the conspiracy framing, it is the mathematical one. The finite time singularity result, with its specific date attached, is being circulated in some contexts as a deterministic eruption prediction. Scientists say Campi Flegrei will erupt in 2033 is a sentence that can easily appear in a headline, and it is wrong in every important way. The singularity is a regime boundary, not an eruption forecast. The confidence interval is a statistical range on a mathematical parameter, not a window for a specific physical event. The uncertainty about what happens at the boundary is genuine and fundamental, not a hedge. The misinterpretation matters because it has real consequences. Misinterpreting T sub C as an eruption date could cause people to make life decisions about whether to stay in Pozzuoli, about property values, about the trustworthiness of official communications, based on a fundamentally incorrect reading of what the science is saying, and ironically, misrepresenting the science as more deterministic than it is, and then having the predicted date pass without the predicted event, damages public trust in volcanic risk communication precisely at the moment when that communication is most important. The actual picture is more nuanced and, in some respects, more concerning than the eruption in 2033 narrative. It does not say, nothing will happen until 2033. It says the system is already in a fundamentally changed regime, that it is heading toward a boundary, that the boundary's physical outcome is uncertain, and that the window for meaningful action, in terms of preparation, planning, and monitoring, is the current one, that is harder to fit in a headline. It is also the truth. The conspiracy and alternative frameworks always circle back to the same error. They replace the genuine complexity of a singular dynamical system with a simpler story that either minimizes the risk or catastrophizes it into a specific predetermined event. The reality of Campi Flegrei is more interesting and more challenging than either of those stories. It is a real system, driven by real physics, approaching a real mathematical boundary, with a genuinely uncertain but genuinely important range of possible outcomes. Understanding that fully is harder than a conspiracy theory. It is also more useful. Part 14. Is this part of a global pattern? Let me address a question that frequently accompanies any reporting on unusual volcanic activity, and one that has already started circulating in the comments sections and forums wherever this study is being discussed. Is this part of something larger? Is there a global pattern of volcanic unrest that makes Campi Flegrei's situation one piece of a broader phenomenon rather than an isolated case? Are the volcanoes waking up together? It is a natural question. Human beings are pattern recognition machines. We are literally wired to find connections, to spot clusters, to construct narratives that link apparently separate events into a single coherent story. It is one of the most useful cognitive tools our species has ever developed. It is also, when applied carelessly to complex natural systems, one of the most reliable ways to be wrong in an interesting direction. The short answer, based on the available data, is no, at least not in any causally meaningful sense. But the long answer is worth working through carefully, because understanding why Campiflegrei is not part of a global pattern is actually what makes it more significant, not less. The specificity of what is happening beneath the Bay of Naples is the point. Diluting it into a vague planetary narrative would be the wrong move, and here is why. At any given moment on this planet, between 40 and 50 volcanoes are in some state of elevated unrest or active eruption. 40 to 50 simultaneously. Right now, as you watch this, that number does not represent a crisis. It represents the normal operating state of a geologically active planet. The Earth's volcanic systems are not static features, waiting to be switched on by some external trigger. They are continuously evolving, continuously pressurizing and depressurizing, continuously fed by the slow churning of a mantle that does not take days off. The apparent clustering of notable volcanic events in any given year or any given news cycle is, in most cases, a function of three things: increased global monitoring capacity that catches events previous generations would have missed entirely, social media amplification that makes every significant earthquake swarm in a monitored system immediately visible worldwide, and the very human tendency to remember the hits and forget the misses when looking for patterns. None of those three things are evidence of coordinated global volcanic activity. They are evidence of a more connected, more monitored, more attention-saturated world overlaid on a planet that was always this volcanically busy, even when we were not watching closely enough to notice. So when someone tells you that Campiflegrei is part of a broader awakening of the Earth's volcanic systems, the honest scientific response is to ask them what baseline they are comparing to. Because the baseline, when you actually look at it, is already quite active. The perceived anomaly often dissolves when you account for observation bias. That said, let me walk through the specific systems that most commonly get mentioned in the same breath as Campiflegrei, because some of them are genuinely interesting in their own right, and the comparisons are worth addressing directly rather than dismissing wholesale. Yellowstone is the one that comes up most often, with the most dramatic framing. The supervolcano beneath the Yellowstone caldera in the western United States has an almost mythological status in popular science communication, partly because of its genuine geological significance. The last major eruption cycle there, roughly 640,000 years ago, was a continental-scale catastrophic event, and partly because it is located in a wealthy, highly monitored country with excellent media infrastructure for amplifying anything that sounds alarming. Yellowstone gets a lot of coverage, but Yellowstone's current monitoring data tells a story of entirely expected, entirely normal behavior for a large caldera system in a period of background activity. Its deformation cycles include both uplift and subsidence of up to several centimeters per year, depending on which part of the caldera you are measuring, and those cycles are well within the range of its documented historical variability over the monitoring era. There is no singularity class acceleration in the Yellowstone deformation record. There is no transition from elastic to inelastic rock behavior, analogous to the 2022 shift at Campiflegrei. The two systems are simply not comparable in terms of current dynamical state, and treating them as parallel cases, because they are both large calderas with supervolcanic histories, is a category error. One of them has a mathematical horizon identified by a finite time singularity model. The other one does not. That difference is not a detail. It is the entire point. The Reykjanes Peninsula in Iceland is a more genuinely anomalous case, and it deserves more careful treatment than a simple dismissal. Since 2021, the peninsula has experienced a series of volcanic eruptions in an area that had been quiet for roughly 800 years. That is a real geological anomaly for that specific location. The reawakening of a volcanic system after 8 centuries of quiescence reflects a genuine change in the state of the volcanic plumbing feeding the Reykjanes system, and Icelandic volcanologists have been clear that this represents a new eruptive period that could continue for decades. But the mechanism driving Reykjanes activity is fundamentally different from what is happening at Campiflagray. The Reykjanes Peninsula sits directly on the mid-Atlantic spreading center, the diverging boundary between the North American and Eurasian tectonic plates. Its volcanism is driven by rifting, by the lateral pulling apart of the crust as the plates separate, which allows magma from relatively shallow sources to intrude upward along the rift zone. It is a completely different tectonic and volcanic setting from Campiflagray, which is a large caldera system driven by deep volatile flux in a crustal magma body with a complex overlying hydrothermal system in a region associated with the subduction of the African plate beneath the European one. The two systems share the characteristic of being active and currently changing. They share essentially nothing else in terms of the physics driving their behavior. Pointing to both of them as evidence of a global pattern would be like pointing to a forest fire and a house fire as evidence of a coordinated arson campaign, because both involve combustion. Kilauea in Hawaii is perhaps the most frequently cited comparison when people want to frame volcanic activity as globally unusual, mainly because it is highly visible, frequently photographed, and produces the kind of dramatic lava imagery that spreads rapidly online. But Kilauea has been erupting, with brief pauses, more or less continuously for decades. It is not a dormant system suddenly reactivating. It is one of the most persistently active volcanoes on Earth, fed by the Hawaiian hotspot, a deep mantle plume that has been punching through the Pacific plate for millions of years and building the Hawaiian island chain one eruption at a time. Its volcanism is basaltic and effusive. Its dynamics are completely unrelated to caldera system behavior. Comparing Kilauea to Campiflagray, because they are both volcanoes currently doing volcanic things, is roughly equivalent to comparing a running garden hose to a building with a cracked foundation, because both involve water. The reason I am taking the time to walk through these comparisons carefully is not to be dismissive of global volcanic monitoring as a field, or to suggest that understanding large-scale patterns in Earth's volcanism is unimportant. It absolutely is important. The reason is to make a very specific point about Campiflagray, and it is a point the new study makes implicitly by the precision of its methodology. What makes this system significant right now is not its membership in any global anomaly. It is its specific, dynamical state, the finite time singularity behavior, the 2 decades of accumulated inelastic damage, the 2022 phase transition from elastic to irreversible rock deformation, the convergence of 2 completely independent datasets, GNSS deformation and Benioff strain seismicity, on a common critical horizon of approximately 2033. The transfer entropy analysis showing that deformation drives seismicity and not the reverse. The extraordinary inverse time linearization fit with an R² greater than 0.99. These are not generic features of a globally restless planet. These are specific, quantified, mathematically characterized properties of this one system, arising from its particular geological history, its structural configuration, and its current physical state. Campiflagray does not need a global pattern to be the most important volcanic story on Earth right now. It is important entirely on its own terms, by its own mathematics, with its own critical horizon. If anything, embedding it in a speculative narrative about planetary volcanic awakening would actually dilute what makes the new study so valuable, because the value is in the specificity, the precision of the singularity fit, the clarity of the 2022 transition, the tightness of the dataset convergence. Zoom out too far, and you lose exactly the resolution at which the meaningful signal lies. The question worth sitting with is not whether Campiflagray is doing what other volcanoes are doing. The question worth sitting with is this: of all the volcanic systems on Earth being monitored right now, How many of them have had their dynamics characterized at this level of mathematical sophistication, with this quality of data, using this kind of complex systems analysis? And the honest answer is very few, if any, at this level of rigor applied to a single system in this much detail, which means we may simply be seeing Campiflegrei clearly for the first time. And what we are seeing, when we look clearly, is not one volcano in a restless crowd. It is a system approaching a mathematical boundary that no other monitored volcano on Earth currently has a name for. Part 15. The next signals that matter. If the finite time singularity model is correct, if the system is genuinely approaching a critical horizon around 2033, with the outcome uncertain but the boundary mathematically real, then the question for the scientists monitoring it, and for the civil protection authorities responsible for the safety of 1 million people, is the most practical question in this entire discussion. Not the most mathematically elegant question, not the most theoretically interesting question, the most practical one. What do we watch for? What signals will tell us which trajectory the system is actually taking as it moves toward that horizon? And how much warning will those signals give us before the picture changes in ways that demand action? These are not rhetorical questions. The researchers address them directly, and the answers are specific enough to be genuinely useful, which is one of the things that separates this study from a lot of complex systems analysis that identifies problems without providing any operational guidance for what to do about them. The researchers identify several categories of escalation indicators, signals that would suggest the system is moving toward the more dangerous end of the outcome spectrum, and several stabilization indicators that would suggest the approach to the critical horizon might involve a more benign transition. Neither category is a binary switch. Neither category represents a single moment at which everything suddenly becomes clear. They are gradients, trends, changes in the character of the data that a well-designed monitoring framework can detect weeks to months before they become unambiguous to the naked eye. On the escalation side, the single most important signal to watch for is the appearance of log periodic oscillations in the seismic data. I mentioned the absence of these oscillations earlier as one of the key reasons the study does not support an imminent large-scale eruption interpretation, so let me be precise about what their appearance would actually mean. Log periodic oscillations are a specific mathematical pattern that emerges in the behavior of complex systems that are failing through hierarchical fracture propagation. Cascades of damage that move upward through scales, from grain-level microfractures to fractures visible in outcrop to kilometer-scale structural failures. When a system begins failing this way, the oscillations it produces around its accelerating trend follow a pattern with a very specific mathematical signature. The frequency of the oscillations increases as you approach the critical point, but it increases in a precise multiplicative ratio. It is, in effect, the seismic fingerprint of a fracture network that is becoming self-organized, that is developing the spatial coherence and hierarchical connectivity needed to coordinate failure across a large volume. Right now, that pattern is absent from the Campiflegrei seismic catalog. The earthquakes are accelerating. They fit the singularity model, but they are doing so without the oscillatory structure that would indicate hierarchical fracture coordination. The seismicity is still diffuse, spread across the caldera, without the spatial clustering that would trace out a developing failure surface. This is the critical distinction between a system that is accelerating toward a boundary and a system that is organizing for a specific large-scale failure event. When log periodic oscillations appear, if they appear, they will not arrive as a single dramatic signal. They will emerge gradually in the data, initially detectable only through careful statistical analysis, becoming more obvious over weeks and months. This is important because it means the signal is not a last-minute alarm. It is an early warning indicator with meaningful lead time, provided someone is doing the right analysis on the right data in something close to real time. The monitoring infrastructure at Campiflegrei, one of the most extensive seismic networks deployed on any volcanic system in the world, is in principle capable of detecting this transition. Whether the analytical frameworks to identify it are being run continuously and in real time is a different question, and one that the new study implicitly raises as an operational priority. The second key escalation indicator is fracture network connectivity. This is subtly different from the log periodic oscillation signal, though the two are related. Fracture network connectivity refers to whether the seismicity is beginning to cluster spatially in ways that trace out developing fracture surfaces, lines or planes of weakness cutting through the caldera rock, rather than remaining scattered and diffuse across the entire caldera volume. A diffuse seismicity pattern tells you the rock is cracking throughout a large volume under generalized stress. A spatially organized seismicity pattern, clustering along specific orientations and at specific depths, tells you that a failure surface is developing, that the distributed damage is beginning to coalesce into something directional. Modern seismic relocation techniques and tomographic imaging are sensitive enough to detect this kind of spatial evolution if the monitoring network density is sufficient and the analysis is continuous. At Campiflagre, both conditions are approximately met. The technology exists. The network is there. The question is whether it is being used in the right way to catch this specific transition. Third on the escalation list is what the researchers call synchronized acceleration across multiple variables. This is the scenario in which deformation rate, seismicity rate, and geochemical signal changes all begin increasing simultaneously rather than on their partially independent trajectories. Right now, the three subsystems are coupled. The transfer entropy analysis confirms that, but they are not perfectly synchronized. They are running at different rates, with different beta exponents, responding to the same underlying driver with different sensitivities. If a point arrives at which all three begin accelerating together, tightening their rates of change in concert, it would indicate that the feedback loops connecting them are strengthening, that the system is becoming more internally coherent, and that the approach to the critical horizon is itself accelerating. Synchronized multivariable acceleration is, in the language of complex systems, the signature of a system moving from the accelerating but diffuse phase toward the organizing for transition phase. It is not a final warning, but it is a serious one. Now, on the stabilization side, because this is not a one-way street and the outcome space genuinely includes more benign possibilities, and those possibilities also have specific signatures worth watching for, the most significant stabilization signal would be a meaningful and sustained change in the hydrogen sulfide to carbon dioxide ratio in the solfatara fumarole emissions, back toward lower values. You will remember that the rising ratio has been interpreted as evidence of increasing deep volatile input from the magmatic source, more gas arriving from depth, bypassing the hydrothermal scrubbing that would normally remove hydrogen sulfide before it reached the surface. A reversal of that trend would suggest that the deep volatile flux is decreasing, that the magmatic source at depth is contributing less to the hydrothermal system, that the primary driver of the feedback loop is weakening. It would not mean the danger had passed. Accumulated inelastic damage does not disappear because the pressure input decreases, but it would mean the engine driving the acceleration was running lower on fuel, paired with a geochemical reversal. The other stabilization signal to watch is an uplift rate plateau or reversal in the right GNSS record. A flattening of the curve, the rate of vertical ground movement decreasing towards zero, would indicate that the pressure source inflating the crust is no longer pushing as hard. An actual reversal, the ground beginning to subside, would be the clearest possible signal of a deflationary scenario beginning. These two signals together, geochemical reversal plus deformation deceleration, would be consistent with the system stepping back from its current trajectory. They would be the most reassuring combination of observations possible within the current monitoring framework. They would not be a guarantee of safety. The accumulated damage and the proximity to the critical horizon would still demand serious attention, but they would represent a genuine change in trajectory rather than a continuation of the current one. Here is the insight that ties all of these signals together into a coherent monitoring framework. None of them are binary. None of them flip from absent to present in a single moment. They exist on spectrums. They evolve gradually. And because they evolve gradually, in a well-monitored system with a well-specified mathematical baseline, they are detectable before they become unambiguous. This is what the singularity model provides that no previous analytical framework for Campiflegrei has provided: a quantitative baseline precise enough that deviations from it in either direction, toward escalation or towards stabilization, are immediately meaningful. Every new data point from Wright, every new earthquake in the catalogue, every new fumarole measurement from Solfatara is now a data point that can be evaluated not just against historical averages, but against the specific predicted trajectory of the singularity model. Departures from that trajectory, either accelerating toward the boundary faster than predicted or decelerating away from it, are detectable in real time. This is what real-time model updating actually means in practice. Not a single forecast produced today and archived until 2033. A living, continuously revised probabilistic assessment that gets smarter with every observation and flags meaningful changes in system behavior as they develop, not after they have already become a crisis. Somewhere in Pozzuoli right now, the right antenna is measuring the ground, centimeter by centimeter. The data is arriving. The math is running. People are going to work, walking past the harbour where the boats sit at angles that were not quite right 20 years ago, sending their children to schools built on rock that is weaker than it was when those schools were constructed. The math says the current regime ends around 2033. The math does not say what replaces it. The physics says the rock has been permanently changed. The physics does not specify when that change becomes a crisis. The monitoring data says the system is accelerating and coupling and entering territory it has not occupied in nearly 500 years. The monitoring data does not say the crisis is tomorrow, but it does say this, clearly and without ambiguity. The optimal window for meaningful preparation is not when the picture becomes clearer, because in a singular system, the picture becomes simultaneously clearer in some ways and more uncertain in the ones that matter most as you approach the boundary. The optimal window is now, while the trajectory is still in its more predictable phase, while the signals are still gradual enough to be read carefully rather than reacted to urgently. 1 million people, one mathematical horizon, one window that, according to the equations, is already open and will not stay open forever. Part 16. The clock without an event. I want to end where the science ends, because the science ends in a place that is genuinely difficult to hold in the mind. Not because it is frightening, though it is. Not because it is uncertain, though it is that too. But because it places human consciousness in an unusual relationship with geological time, and that relationship, when you look at it honestly, says something unsettling about the nature of risk and knowledge and what we do with both. It asks a question that volcanology cannot answer, that physics cannot answer, that mathematics, for all its precision in this study, cannot answer. It asks what human beings do when they know a boundary is coming and do not know what is on the other side of it. That is not a comfortable place to sit, but it is where the data has brought us, and I think it deserves to be examined honestly rather than smoothed over with either false reassurance or dramatic catastrophism. We have built cities on volcanoes since the beginning of civilization. This is not a modern mistake or an ancient one. It is a continuous, rational, pragmatic choice that has been made by human communities on every inhabited continent for as long as there have been human communities to make choices. We have done this because volcanoes, the soil above them, the trade routes through them, the thermal resources within them, the harbours formed by their ancient flows and collapsed calderas, have always been more useful to human life than they have been dangerous. On average, statistically, over most of history, the calculation works out, most of the time, for most people, across most of the geological record. The people of Pozzuoli did not build their city on top of Campiflegrei in ignorance of the risk. This is important to understand. because there is a tendency in modern risk communication to frame populations living near volcanic hazards as somehow unaware of their situation, as if the solution is simply better education. The Romans who built the Macellum, the fish market whose columns still stand in the harbour, scarred with the borings of marine mollusks at heights far above the current waterline, silent testimony to how many times this ground has risen and fallen. Those Romans were not ignorant. They were making a calculation. The harbour was exceptional. The fishing grounds were productive. The thermal baths fed by the geothermal system were a source of wealth and health. The soil of the surrounding agricultural land, fertilized by millennia of volcanic ash and mineral-rich water, was among the most productive in the ancient Mediterranean world. 3,000 years of continuous human habitation on the Campi Flegrei caldera is not evidence of ignorance. It is evidence of a trade-off that, for 3,000 years, kept paying out on the right side of the ledger. What the new study is telling us is that the terms of that trade-off are changing. Not because the system has suddenly become volcanic, it was always volcanic, and everyone who ever lived there knew it, but because the specific dynamical state of the system has entered a regime that is mathematically distinguishable from anything in the modern monitoring era, and possibly from anything since the eruption of Monte Nuovo in 1538. The same equations that describe the approach to phase transitions in material science, the moment a metal under stress crosses from elastic deformation into irreversible fracture, now fit the data at Campi Flegrei better than the equations volcanologists have trusted for 40 years. The same mathematical structure that describes critical transitions in financial markets, in ecological systems on the edge of collapse, in the behavior of complex networks approaching a reorganization threshold, that structure is what the ground beneath Pazuli is now tracing in the data. That is a sentence worth sitting with. The ground beneath a city is behaving like a complex system approaching a phase transition, not metaphorically, mathematically, with a fitted model and an R² greater than 0.99 and a critical horizon with a 95% confidence interval. The finite time singularity is not a prophecy. I want to be clear about that one final time, because the temptation to read it as one is real and understandable. It is a description. It describes a system that is approaching the boundary of its own current behavior, the point at which the governing equations of the present regime cease to be valid and something new must take their place. It describes a system that has a clock built into its mathematics, and it is careful enough, rigorous enough, and honest enough to say exactly this and nothing more. We know the clock is running. We do not know what it is counting down to. That combination, certainty about the existence of the boundary, genuine uncertainty about what the boundary contains, is one of the stranger epistemic positions that science can find itself in. It is more honest than a false precision that would give you a specific outcome prediction dressed up in statistical clothing. It is more useful than a shrug that says, volcanic systems are complex, we cannot know anything, move along. But it does not give you the clean narrative closure that human psychology tends to demand when the stakes are high. It does not say, evacuate by this date. It does not say, you are safe until that date. It says something harder and more demanding than either of those. The system you are living on is entering unknown territory. The entry window is approximately now through the early 2030s, and the outcome space includes several possibilities of varying severity and exactly zero possibilities that look like the last 20 years continuing unchanged. Zero. The mathematics rules that out completely. Whatever comes next, it will not be this. Think about what that means for a moment. Not for the scientists, for the people, for the 75,000 residents of Pozzuoli going about their lives above the center of the deformation field, for the 3 million people in Naples whose eastern districts lie just outside the caldera rim, for the families who have lived in this region for generations, whose relationship with the burning fields is not an abstract hazard assessment, but a lived daily reality of cracking streets and tilting harbour walls and sulphur smell on hot days, and the particular quality of light over a bay that sits inside the ruins of a supervolcano, The columns of the mycelium are still there in the harbour. You can go and look at them. The borings of the marine mollusks, the lithophaga, the date mussels that drill into submerged stone, are visible at roughly 6 meters above the current waterline. 6 meters. Those borings are a geological record of how high the sea level was relative to this ground during an earlier submergence phase, when the caldera had deflated enough that Pozzuoli sank below the waves. And what followed that submergence, eventually, was the uplift that preceded the eruption of Monte Nuovo in 1538. The columns are not just a tourist attraction, they are a stratigraphic record of a system that cycles, that rises and falls and rises again, and that has, at least once in documented history, risen far enough to produce a new volcano. The math has identified a horizon approximately 8 to 9 years away. The system on the other side of that horizon is unknown, but the system on this side of it, the one we can currently describe, measure, model, and monitor, is already in a state without modern precedent, already past the phase transition of 2022, already carrying 20 years of irreversible structural damage, already tracing the mathematical curve of something that ends. What we do with that knowledge is genuinely, uncomfortably, not a scientific question. How we prepare for a boundary whose physical contents we cannot specify. That is an emergency management question, a political question, a question about resources and timelines and the psychology of communicating probabilistic risk to populations who reasonably want to know whether they should leave. How we communicate a risk that is real and non-trivial but non-deterministic, that is a public health communication question, a media ethics question, a question about the difference between informing people and alarming them in ways that produce worse outcomes than the hazard itself. How we make decisions about 1 million lives in the shadow of an equation that has a date but not an outcome, that is a moral question. A question about what we owe each other when the numbers are telling us something serious but not something simple. The volcanologists have done their part. The study is published. The mathematics is available. The critical horizon is identified. The signal indicators are specified. The monitoring infrastructure exists. What happens next depends on whether the people responsible for acting on scientific knowledge, the civil protection authorities, the government planners, the local administrators, the media that communicates risk to the public, treat a mathematical horizon as a reason to prepare or as an excuse to wait for more certainty that the mathematics itself predicts will not arrive in the form anyone wants. The ground is still moving, the data is still arriving, the equations are still running, and somewhere beneath the Bay of Naples, in the rock that has been cracking and fracturing and accumulating irreversible damage for 20 years, a system is approaching the end of what it has been and the beginning of whatever comes next. We are watching in real time. For the first time in recorded history, we have the mathematics to know that we are watching a singular system approach its own horizon. Previous generations who lived above Campi Flegrei felt the earthquakes, smelled the sulfur, watched the harbour rise, and did not have the language to describe what the system was doing at the level of its underlying dynamics. We have that language now. We have the model, we have the fit, we have the date range, we have the signal indicators that will tell us which way the system is trending as it approaches the boundary. The only question that remains, the one the equations cannot answer, the one that falls entirely to us, is whether we have the wisdom to act on what the numbers are telling us before the numbers change in ways that leave us no room to act at all.